There we go. Okay. So this unit, everyone listen up. This unit, again, did forces still relate to kinematics? Of course it has to be. Just like math, everything in physics is connected, okay? The more complex the problem gets, means you have to actually look at the big picture and see how you can connect things together. So this unit is divided into two big themes. The first theme is what? Work and energy, or most likely, what's the biggest word in here? Energy is actually the biggest concept, okay? And then we're gonna do the second topic, which is what? Which is momentum, okay? So today we start with the basics of one of these, which is what? Which is work. How many people remember work from grade 11 physics? Here's the good news. Exactly the same lesson. Energy starts getting more complex in grade 12. The idea of work is still exactly the same thing. In fact, if you look at the notes, you're gonna see that it exactly looks like the what? The same notes we got from grade 11 last term. Okay, so let's start. Okay, so work. Okay, so what's the definition of work in a physics context? In a physics context, the definition of work, go ahead, copy that down. The definition of work is that it's a physical quantity that is always a result of two things. Work is always the result or the outcome or the effect. Effect is different to cause. Cause happens first, effect happens after. Is the result of what? Of the application of a force. The application of a force. By the way, that doesn't mean that it only applies to force applied. No, it just means to the existence of an applied force by something. Could be the. By the way, what do you call applied force by Earth? Exactly. So technically, all forces are applied. It just, some of them are applied by certain things that we give them special names. Fg is the force on an object applied by the Earth. Fn is the force on an object applied by a surface. F friction is the force on an object applied by a surface when you go along or across from it. So on. The application of a force on an object and displacement. Okay? Displacement has to exist, or motion has to exist for work to be what? For work to be actually present. This is a very important thing. Okay? So this basically says one of two things. If you have no force being applied, there is no work, and get used to this, everyone. No work being done. Force is always what? Force is always what? Force is always applied. Work is always what? Work is always what? Done. You never do force. You what? You apply force. You never apply work. You what? You do work. Work is done. Everyone, this is important to understand because it even matters to the concept. Work is always done. Force is always applied. Work is never applied. You never say, you applied 5 whatever of work. No, you did 5 calories of work. Okay? By doing what? By applying 7 newtons of force. Okay, so always remember, force is applied, work is done all the time. I don't care what physics you ever see or do, you will never see it flip the other way around. So if there's no force being applied, there's no work. I want you to write being done or just done. No work done. By what? Go ahead. Uh-huh. Being done means, okay, see, that's why we have to wait until we do energy to really understand the meaning of work. It means that no energy is being burned. Remember, work and energy are really the what? Are really the same thing. Okay, question. Who remembers the unit for measuring both energy and work? Exactly. What is it? Say again. Joules. And if two things are measured in the same unit, aren't they necessarily the same thing? Yeah, kind of like what? Displacement and distance. They are different, but at the end of the day, could they still be related? Same thing with work and energy. That's the idea. Okay, so no work being done means no energy was what? Was burned or expended. So the other thing is, if you do force, but you still see what? No displacement, like no motion happened, that means what? No work was done on the object that did not move. On the object that did not move. There has to be motion present for work to be done. Okay. Who remembers this one? I mentioned it so many times, and it is the first thing that comes to mind. What's the physical symbol for work? Not the unit, the mathematical physical symbol. Uppercase or lowercase? Usually uppercase. I love using it uppercase because to me lowercase w is like width in math. But I've seen physics textbook where if you have multiple works being done, instead of calling it W1 and W2 and W3, which is my style, they call it capital W and small w. Either way, it's a W. What can you tell about this symbol? It's a what? It doesn't have a what on top. It doesn't have an arrow. So work is always what? Work is always a scalar, which is weird because it involves doing what? Sorry, applying what? Which is by nature a what? And having what to experience, which is also what by nature? You are combining two vectors, and yet you're getting a what? You're getting a scalar. Did anyone here finish? Sorry. Okay, how many people? Okay, how many people are taking calculus and vectors right now? Did Mr. Shivers start vectors yet or not? You okay? How many people finished MCV for you? Uh-huh. Do you remember something called? And again, I don't want anyone to remember this one. I'm just mentioning it because you're gonna see it in what? In calculus and vectors. Do you remember something called the dot product and the cross product? Do you remember by chance? You remember hearing it and you remember seeing it. Yes, everyone. In math, you will learn something extremely important in calculus and vectors. Actually, I should say just vectors. That two vectors could be combined, yet you get what at the end? You completely eliminate what? The direction from the calculation you're doing. And there are other calculations where you still combine them and you get what at the end? No, this a vector. So everyone, when you, okay, question for you. What's 5 times 3? No tricks. What's 3 times 5? What's the interpretation of 5 times 3? What does it mean to say 5 times 3? 5 boxes of 3 things. Or 3 boxes of, there is no other way to understand 5 times 3. Here's the thing when you multiply two vectors. There is a way to multiply them to produce a what? A scalar. And there is a completely different way to multiply them and to produce a what? A vector. Depending on what you want to produce, you multiply them differently. And that's all I'm going to say. I can't teach you any more. I would love to. I can, because that's what first year physics is for, or like. But you have to wait until what Mr. Shivers actually tells you the dot product and the what? The cross product. Okay, you'll understand why they're called like that. Okay, so it's a scalar. It must have no direction. It must have no direction. Okay, all right. Okay, so let's go to the next slide. Okay, the mathematical formula. Now, again, touching back to the idea of dot product and cross product, there are two ways to define the mathematical formula for work. One that you will see in calculus and vectors, and you will see next year in first year physics, and one that does not involve vectors, which is the one I am obligated to show you, because remember, what is the only math requirement for grade 12 physics? No, not even. Only grade 10 academic math, which does not cover what? Vectors and all of that stuff. So I have to teach you the what? The vector-free way of doing what? Of calculating work. Mr. Shivers, and next year, we'll teach you both the vector-free way and the vector way of doing it. Here is the formula. Boom. Officially, you only need grade 10 math to go into both grade 11 and grade 12 physics. Yes. Which is fine. But not math 11 to go into physics 12. You see what I mean? You need math 10 to go into physics 11. So you think, oh, I need to push each one up a stage. No, math 10 is still the requirement for. That's why there are so many things in grade 11 math, MCR3U, that I can't use in this course because I can't guarantee that everyone took it. I mean, by logic, almost everyone here took 11 math, but it's not officially a requirement for covering grade 12 physics, which is good. We're keeping the math to a minimum. Yes. Oh, I'm not talking about 100%. But again, you would not be accepted until you cover what? Grade 11, grade 12 functions, and grade 12 calculus. Yes, you're right. But grade 12 physics, no. So the formula for work is what? 3 things multiplied together. Force being applied, distance being moved, or displacement being moved, if you like. And then the what? The cosine. The cosine. The cosine of the inside angle. Now, why am I saying the inside angle? Okay, humor me for a second. Pencils down, everyone. Let's say, okay, I want you to, are those two vectors the same? Are those two vectors identical? Why not? What two things are different between the two of them? Give me just one thing that they don't have as the same between them. They don't have, I sketched them on purpose not to point parallel to each other. So right off the bat, they don't have the same direction. Also, they don't have the same what? Length, magnitude, size. So that means they are definitely, sorry, not the same vector. My question to you is, I want you to connect these two. Now, how many ways can you connect any two vectors? Okay, hint. Remember the two ways of adding vectors that I taught you in kinematics. There are two ways to add any two vectors. A way we learned first, and another way we learned that we almost said we're going to use it until the end of this course. What was the name of the first method? The cosine law method. Okay, the cosine law method. How do you do the cosine law method? Like, what do you do? How do you connect them? It's everyone, pencils down. Just focus here. It's really important how you connect them. How do you connect them in cosine law method? Remember how you connected the vectors in a relative motion question. Did you no? Did you connect them tail to tail or head to tail? Head, tail to tail would be the other method. You make them all come out of the same origin. So my question here is, I can either put this one in front of this one, right? Or I could make this one in front of this one. All right. I'm going to try to mimic this guy because I don't think I can move it. Yes, yes. Which because the way you connect them is going to define if you're using what, cosine or, there you go. That's actually the difference. One of them gives you a scalar and one of them gives you a what? A vector. Okay. Again, I don't want you to overthink this. I'm just extending, but to really, because you know me, I never tell you, oh, believe me, this is why it happened. I try to explain a little bit. So my question now is, can someone guess what this angle is? By the way, any logical guess is accepted. Obviously, is this a sharp? Not sharp. What's the acute or an obtuse angle? Obtuse angle. So let's pick a number here. Obviously, it's not 180, but it's kind of close. So what could it be? How many? How many people want to do 150? Yeah, I mean this is kind of 150. Okay. All right, everyone, get me the cosine of 150. Come on, get me the cosine of 150. We need a cosine of 150. I know it. It's negative what? 866, which according to radicals, do you know that's what? Because, by the way, there's a reason I picked 150. Because 150 is related to 30, right? Because what's 150 plus 30? 180. It's the so it's a supplementary of it, okay? But what was the answer? Positive or negative? Okay. Now I want you to imagine if we did not connect them head to tail, if we connect them what? Tail to tail. So that means instead of putting this one here, where am I going to put it? I'm going to put the two tails to touch each other, right? So I'm going to move this one such that this tail touches this tail. So what's this angle now by default? Remember the F theorem? How many people remember the F theorem? Isn't that an F or a C? What does that tell you? This angle plus this angle have to be what? 180 degrees, right? As long as these two lines are what? Thank you. Very good. All right. So my question now is, what's the cosine of 30? It's the same exact number as the cosine 150, but it's instead what? Instead of negative, it's what? And that's why it's what? It's very important to know if you connect them what? Head to tail or? Because one time you could get what kind of work? Negative. And one time you could get what kind of work? Do you think it's important to know what kind of a sign you have work for? Yes, because you're either losing energy or what? There you go. You see, it all builds up at the end. Now, here's the thing. What are we doing? We're doing the cosine of what? What do you think I mean by inside angle? I always like my word equations to have like a physical meaning to them. What do you think I mean when I say inside angle? How many people think it's tail to tail? It is tail to tail, because to me, when you hold two vectors, to me, this angle, once they go tail to tail, this angle is inside both of them, right? It's constrained between both of them. Here, it's not inside because basically that's the head and that's the tail. Okay, so always, always put the vectors which way in these problems? Tail to tail. Otherwise, you're always going to get the same answer, but with what sign? The opposite sign of what you want, which means your full answer could lead you in completely different what direction, because it could tell you, oh, am I losing energy? You are, but then you think you're what? Which violates a very important principle in nature. What is it? Conservation of Conservation of energy, exactly. You might think you're losing, but you end up gaining, which doesn't make sense. Yes. Yeah, yep. In a way, yes, that's how they're related. And Mr. Shivers will expand much more on it when he actually shows you why that actually happened. Okay? All right. So what would this be in mathematical terms? Boom. That's it. Done. Capital W equals force as a magnitude. Everyone, by the way, just so you know, listen up. This equation really, I don't want to say it doesn't depend on direction, but the direction is here because you already dealt with the what? You already put the directions on the vectors. What really matters now is how much force you're considering and how much distance you're considering as well. Okay, question for you. Almost every FBD I gave you for like 4 weeks straight, how many did it have one force on it or multiple forces? Multiple forces. Here's the thing. Technically, if I show you any FBD, I could ask you for the work done by what? By each single force of these forces. So if you have, for example, if you have four forces, how many works could I ask you for? Four work. I could ask you for the work done by force gravity, the work done by force applied, the work done by force. By the way, is there such a thing as what's the work? What's the work done by the force of static friction? Does static friction ever do work? Why not? Which one of the two conditions on the first slide is it violating? We said no, on the first slide, you're thinking way too much. We said that for work to be done, a force has to be applied, but also what? Displacement has to be experienced. Static friction only deals with what kind of object? An object that has not moved yet, which means can you ever get the work of static friction? How about the work of kinetic friction? Yes, of course, because it's stealing energy from the system. Nice. Okay? So technically this equation, everyone, becomes like this. Go ahead. So I could have WG. Okay, what are the subscripts we dealt with so far in this course? Let's just write them here. We dealt with G. We dealt with N in any order you want. We dealt with N. We dealt with K for kinetic. And we dealt with app. And we dealt with technically what? Tension as well, yes. Which means the same exact subscripts here. Done. There you go. For the angle, you have got to place them tail to tail. Okay? All right. We're good? Okay. So, what was the physical unit for measuring any work again, or energy for that matter? Joules. Have you seen joules in chemistry as well? Yes, you do. Although chemists like to use another unit. It's the same unit that you measure energy in foods. Calorie, yes, calorie. By the way, does anyone know the conversion between calories and joules? Like how much of one is the other? Anyone knows it? Okay, 1 joule, everyone. Sorry, 1 calorie is 4.814 joules. So roughly how many? 5 joules, roughly. Okay. So if someone says I burned 100 calories, that means they roughly burnt how many joules? 500. You got it. 481. All right. Is the joule, and it's a name of a person, so it has to be a capital J, just like capital N was for newtons. Okay. So let's look at the defining equation for work. What was the defining equation for work again? What times what times what? Technically three things. W equals force times displacement or distance times the cosine. All right. All right. Do you remember how we define a unit? I write the equation first, and then I replace what with what? I replace each symbol with its own what? With its own unit. That's the easiest way to define any unit. Okay. How do you measure forces in standard system? Newtons. How do you measure distance or displacement? How do you measure cosine or sine or tan? Ooh. Which one has a unit of degrees? The angle or the cosine or the sine of the angle? Everyone, sine, cosine, tan. Does anyone remember the other three? Secant, cosecant, and cotan, but we don't really care about them. But what do you call sine, cosine, and tan? Trig what? Trig, not functions if you graph them as a wave. There's another, the main name for them. Trig, what's another name for a fraction? Ratios. When you divide a ratio, what happens to the units? Do you remember the mu s and the mu k? Do the mu s and mu k have units? Why not? Because what happens to the units of force? Can someone, okay, tell me what's the sign is, according to SOHCAHTOA. Sine is equal to what over what? Opposite over hypotenuse. What's the opposite measured in? Let's say centimeters. Then also the hypotenuse has to be measured in what? Centimeters. What happens to centimeters over centimeters? They cancel. I swear, if you go right now to first year calculus and you ask a bunch of students randomly, what's the cosine of 45 degrees? They might tell you, they might actually be able to tell you, oh, it's 1 over root of 2. And you play reverse psychology with them. Tell them 1 over root 2 what? What's the unit? And they would like, degrees. They really have no idea what they're talking about. But you just played with their safety net because you're like, what unit is it? And they're like, oh, degrees. And then you go, but I just told you 45 degrees. They're like, oh, meters. And they just start giving units. And they completely forgot the essence of the definition. It's called trig what? Ratio. It's supposed to cancel out. So cosines and sines and tans and all the ratios have what units? No units because they cancel out. Good. Okay. So there we go. Because again, trig ratios have no units. Trig ratios have no units. So can someone now define the joule for me? Can someone now define the joule for me? Just look at that equation and define the joule for me. By the way, do we still have the 1:1:1 ratio? Like we did the 1:1:1 with the newtons and kilograms and meters per second? Yes. Who would like to bother defining the joule? You know what? I'll start you off. The joule is the amount of work that you do when what happens? Literally, all the definitions start like this. The joule is the amount of, the 1 joule is the amount of work that happens when, who would like to finish? Ammar. Well, I want you to use that equation. See, that's the whole idea. I write the equation and then I verbally stretch it out. Okay. No, you 1 Newton of what? Uh-huh. Applied over how much distance? There you go. You see, you can't just say 1 Newton. You have to tell me 1 Newton of what? Applied over 1 meter of what? Done. That's it. There you go. That's how you always define any unit, as long as you have the equation. Yes, hello? Sorry, who? Shira. Okay. Thank you. No problem. So 1 joule, if someone says, I burnt 1 joule of energy or work, that means they applied 1 force, sorry, not 1 force, 1 Newton of force, 1 Newton of force over how much distance? 1 meter exactly of distance. Has anyone, by the way, has anyone heard of the word calibration? When you calibrate, if you ever become an engineer or a technician or a scientist in general, you will hear about the word calibration. Does anyone know what calibration is? Okay, I'll give you a hint. What kind of scale usually do pediatricians use? Pediatricians, what do they, when you were a kid, or when you take your younger sibling to the doctor, like my dad, what kind of scale do they use usually to weigh kids? It's not a digital scale, although some use, but there's another one. What's the old kind of scale, especially at some gyms? It's the what? It's exactly, it's the sliding scale. Okay, before you step on it, do you just step on it, or do you have to do something to it first? You have to what? You have to zero it. Why? Because you have to make sure that it's not what? Adding or subtracting already before you what? Before you step on it. Because if you step on it and it was already added, it's just gonna what? It's gonna give you a higher weight, right? If it was already less, it's gonna what? Give you a lower weight. So what do you always make sure it's what? It's perfectly what? Zeroed out. That's called what? When you calibrate, you make sure that the device is what? Is correct, reset, and made sure to what? To be used. Yes?
Good morning.
Hello?
Just looking for attendance.
Sure,
Please.
no problem. Okay. All right. Oops, sorry. Okay. By the way, is there another way to define this instead of using 1, 1, 1? Remember, there's how many ways to define the 1, 1, 1 relation? Like, do you need to use 1, 1, 1? Do you need to? No. As long as you're trying to produce 1 here, what must happen to these two numbers? It's a balancing act. So if this one was 2 newtons, you cannot apply it over 1 meter. You only have how much distance to apply it over? Half. If this one doubles, this one what? Half. If this one triples, this one what? And so on. As long as you're trying to produce what? 1 single joule of work. Okay. All right. Pencils down. Now, remember when I showed you that the cosine could be what? Positive or? But I showed it to you because you either could place it tail to tail or what? Or head to tail. Well, guess what? You can still get it negative by placing it what? Correctly what? Tail to tail. And let's actually prove. Okay, so due to the cosine term in the formula for work, there are 5 possible outcomes. By the way, some teachers teach them as 3. I like to teach it as 5 because I like to expand more explicitly into the cases, okay? And you see what I mean by that. There are 5 possible outcomes for the work done by any specific force on an object in the FBD. Number 1, I like to call that work fully positive. Fully positive. That only happens in one case, when the theta in the system is exactly how much? 0 degrees. I'll explain what that means. Then, instead of fully positive, I like to call it partially positive. I'll explain what that means. Partially positive. Now your angle is not 0, but it's between what and what? Between 0 and 90. And is it touching either one of those boundaries? Is it less than or less than and equal? Exactly. So that means what? It is definitely above what? Above what? Above 0. So it's not, because we already had a case for the 0. We've already allocated a complete case for the 0. But it's also not touching what? Not, so it's neither touching 0 nor touching 90. What do you call an angle between 0 and 90? Acute angle. Okay. Then it hits perfectly what? 90, which means then the work hits exactly what? 0. Okay. What do you think the next case is? We've done fully positive, partially positive, 0. There are only 2 more cases. Partially negative. Why? Because now my angle is opening up. Now I went beyond 90 degrees. But I'm still what? Not where? I still did not touch 180 degrees. I am bigger than 90 for sure. I am less than 180 for sure. Finally, what's the last case? The complete opposite of the first one, which is what? Fully negative, when your angle is a complete protractor. So how much? 180 degrees. Okay, go ahead. These are the 5 cases. By the way, someone says, what if it's bigger than 180? What's your response? So 180 is a straight line. Oh, yeah. So, okay, someone says, Mr. Ramadan, why did you stop at 180? Keep going. You still have what? You still have another half of the circle. They're right, but why do you think I stopped? Ammar. Exactly. The other half of the circle could still be treated as the what? As the top half of the circle, just from what? By looking the other way. Okay, so you only need how much of a circle to understand work? A full circle or just a half? Just a protractor, which is half a circle. All right, everyone, let's do the first one. Okay, so, okay, imagine if you're not seeing this. Sorry, this was supposed to fade in. When a force and motion are exactly what? Are exactly what? Parallel to each other or pointing exactly in the same direction, the angle between the force and the displacement is exactly how much? What's the angle exactly between these two forces? Sorry, these two vectors. The angle. No. I love this. When you show people this, they're like, there is no angle. And you ask them why, because they're like, they're not touching. I'm like, fine. Then you show them this, and they're like, oh, that's 180. How many people agree that this is 180? How about now? How about now? You see, they don't see it when they're not touching. But when you start with 180 and you use their logical understanding of the angle decreasing, they're like, oh, it is 0 because they're perfectly lined up. See, 0 angle doesn't mean that the two things are touching. It just means they're what? By the way, technically, are those still 180 degrees from each other? Do they have to be touching? Because remember, as long as you move vectors but without changing the direction or length, you are okay considering them to be the what? The same vector. Is it making sense? So that's a 0 degree. Now, yes. Okay. What kind of force usually was like this? Remember, we sketched an insane number of FBDs for the last 4 weeks. What force usually pointed perfectly with the motion? Applied force. What else? Tension, as long as you're pulling exactly what? Parallel to the ground, for example. Could friction ever be like that? Could friction ever go with motion? Good, good, good. So, without even knowing numbers, let's actually build up the equation. W equals force times displacement times cosine of theta. What did we say the theta is in this situation? 0 degrees. What's the cosine of 0 degrees? Positive 1, not just 1, positive 1. Everyone, how many people remember the cast rule? The cast rule. Why is the cosine of 0 a perfect 1? All right, let me give you a very quick idea why. A cast rule is what? The XY system with a what? With a circle, right? What's the radius of the unit circle? 1. So this here hits here at 1, hits here at 1, technically hits here at -1, 0, right? And here is 0, -1, and here is 1, 0, and here is 0, 1, right? So when you have an angle of 0, sorry, this is obviously the y, and this is the x. When you have an angle of 0, where are you? By the way, where do we start measuring angles? Always in math. Where? No, origin. Right here. Because remember, it's an angle. It's rotating. Like if there's a bug on this circle, and I say that the bug is at the location theta equals 0, where is the bug? It's on the circle, but where? Right here. What's the cosine of this position? What's the cosine of 0? So what's the sine of 0? Oh, everyone remember, if one of them, if one, either cosine or sine, makes it to 1, the other one has to make it to what? 0 or -1. You see what I mean? So that means, okay, this is 0. And that's why it is, because it's right here. Okay? Okay. Why do you think I called it max positive or fully positive? Question for you. Look, if you're pulling, everyone, if you're pulling on something like that, are you wasting any of your force? Are you wasting any of the directionality of your force? Is your force perfectly pointing where the object is intended to move? Which means, is this force partially optimal or fully optimal? Like, is there even 1% of this force being wasted? Which means what? All the work you're doing, any of it being wasted or all of it being used? All, which means what your work is doing is what? This is the best, the best amount of work to add to the energy of the system. You're not wasting any of it. Okay, what do I do now? What do I do to my angle, everyone? Eyes on my hand. What do I do? I start what? I start opening up my hand, but only up to how many degrees? 89.99999, because I'm not touching what? 90 has its own third special case. All right, so next one. Okay, everyone, before I do the next one, because I don't want to spoil the surprise here. My next one is going to say what? Case 2, and what's my angle range going to be? Come on. No, between what? 0 non-inclusive and 90 non-inclusive. Okay, question. Give me an angle between 0 and 90. Raise your hand. 45. Get me the cosine of 45. Go. Cosine of 45. And give it to me as a decimal or a perfect radical. I don't care. I want it as a decimal to actually know the magnitude. 0.7, 0.7070. Okay, so everyone, can they say the number again? 0.7. Okay, someone else give me an acute angle other than 45. Come on. Big, small, whatever. 60. Get me the cosine of 60. Come on. I know the cosine of 60. It's a perfect 0.5. It's a perfect half. Okay? All right. Give me another angle. 30. Okay. Get me an angle that's very close to 90, but not 90. Go ahead. Get me the cosine of 89.9, which is right here. 89.9. Almost here. What is it? 1.7 times 10 to the negative what? Which is a big or a small decimal? A very small decimal. Okay. Give me an angle that's very close to what? To 0, but not 0. How about 1 degree? Just 1 degree. Get me the cosine of 1 degree. It should be very close to the what? To the full distance, because cosine is always the horizontal distance. All your answers were what? Negative or positive? And all your answers were bigger than 1 or decimals? So, okay, question. When you multiply something by a less than 1 positive decimal, is it multiplying by 100% or less than 100%? When you multiply by 0.7 or 0.11 or 0.38 or whatever, are you getting the full amount or less? Because you're multiplying by what? Which means, is that work max positive or partially positive? Which means, is it all being used or is it some of it being wasted? Now you're getting the idea. Yes, perfect. So here's the next slide. Like that. Go ahead. What kind of force could point like that from an FBD? Applied. Yeah. I mean, who says? Everyone, look. I can pull on this table in 2 ways, right? Well, in multiple ways. If I pull like this, what's my force compared to the direction of motion? They're what? They're parallel. Yes, because I'm intending it to moving this way and I'm pulling this way. How about now? Is it that diagram? Yes. The force applied in my hand is like this, but it moves this way. Perfect. Yes. So that could be force applied. What could it also be? What if instead of using my hand, I use the rope? I use the rope. Tension. Yes, depending on what object you use to pull. So now it's a cosine of acute angle, and the cosine of any acute angle is always a what? It's always positive, and it's always what? Which means you still get a positive number, but what? Because you made it, you multiplied it. Sorry, you didn't make it a decimal, but you incorporate a decimal into it. Okay? Usher, I'll send a mass email when I post the quiz. Okay? All right. 2 cases done. What's case number 3? Case number 3. It's its own case. 90 perfect degrees. Thank you. Everyone, just eyes up here for 30 seconds. When you were at 0 degrees, what was the distance? 1. Then when you went here, for example, is the distance still positive? Yes, it is. But is it 1 or less? And any number that's less than 1 but positive is a what? Is a decimal. Okay? How about when you hit right here? Did you move sideways at all, or did you just move straight up? Okay, what was the distance here? And then what? 0.9, 0.8. You see what's happening? When you hit this, what happens to the distance? It becomes what? You got it. That's why the cosine of 90 degrees is perfect 0. Because you have no what? You have no sideways motion. You're straight up. That's why the cast rule is one of the best math inventions of humanity. It's one of the best visual aids ever. Yes. Yes. It's okay. Again, cosine only relates to what? Sideways motion, which means if you did not move sideways, how much cosine do you have? Because you either moved what? Straight up, or how about sine? Sine doesn't care about sideways motion. Sine only cares about what? Up or down, which means here, how much vertical motion do you have here? None, which is why sine of 0 is 0. How about all the way up here? How much vertical motion do you have? Full. How much full? 1. So that's why the sine of 90 degrees is 1. Cosine is always x, and sine is always what? That's why I always tell you make the horizontal angle, because it's exactly the same idea. All right? Cast rule. Super, super powerful. Okay? All right. So let's do the what? The third case. Third case is exactly this. Boom. A force is perpendicular to the motion. What force could that be, usually? Come on. No. What force? What force could be that? Could be what? Normal. What if I flip the force straight down? It would be gravity. Thank you. So everyone, usually, oh, question everyone. What if you had a ramp? Would force be straight up then? If you had a ramp, does normal force point straight up on a ramp? Straight up on a ramp? No, it's what? Again, as the ramp tilts, the force tilts with it. Okay, good. So I just we said cosine 90 is what? Is 0, which means what? No work being what? No work being done. Okay, everyone, listen up. Conceptual question for all of you. Listen up. Someone says, Mr. Ramadan, that doesn't make sense. You're saying there's how much work? But you are also showing us there's what? You just told us in the first slide that if there is motion and there's a force, there has to be what? There has to be work. How come here you're proving to us mathematically that the work is 0? How do you reconcile this with the first slide? Everyone, give it some thinking. It's really important to understand this. I am seemingly contradicting myself. I told you in the first slide, if there is a force being applied or present and there is motion existent, there has to be work. Yet I am proving to you that there is 0 work here in this situation. That is correct. How come you think it's correct? Because of the formula. You're hovering around it. Keep going. What did I tell you about every force does its own what? Every force does its own work, which means what? Some forces could do what? Positive work. Some forces could do what? And some forces could do what? Could do 0 work. Everyone, think about it this way. The fact that I say 0 work means that force is not supporting the motion or what? Or going against it. Look at that force. Everyone, look at that force. Is there absolutely any component of it sideways this way? Is there any component of it sideways this way? So does this support the motion, resist the motion, or just, sorry. Does this force push it forward, push it backward, or just supports the fact that it goes on this level? Exactly. Everyone, any force. Question, how many forces are on this when I push it this way? The whole time. So one side left it. Nice. One side left it though. One side left it. What force was still on it? What force was still on it? Yet, did they support the motion in any way? No, but they supported that it did not go up or. That's my point. If there's a 0 work for a force, you know one thing about that work. That force. That force is to motion what? Perpendicular to motion. So you can actually tell a lot about the FBD without being given an FBD, just by me giving you the value of work. All right, good. What's my next value? Come on. What's my next opening angle? We're done the entire, everyone, we are done an entire quadrant here. So now we're going into what? Quadrant number what? 2, which is the obtuse side. Any obtuse angle has what kind of cosine? Decimal, but what? But what? Negative. Like I proved to you when you did the cosine of 150. You got negative 0.8666. So that means, question for you, everyone. Look at that FBD. Look at that FBD. Is that force supporting the motion? Sorry. Aiding the motion or resisting it? Resisting, which means, is it adding energy to the system or sucking energy out of the system? Like, is it accelerating or decelerating? If you are pulling on that box that way and it's already moving that way, is there any way you're speeding it up? You're definitely what? And if you're slowing something down, like friction does, are you adding energy to the system or sucking energy out of the system? Exactly, which means your work is how much? Sorry, your work is what? What do you think I mean by less than max? Is this the worst force that could happen to the system? Like, is this the worst resisting force that could happen? What's the worst resisting force that could happen? Exactly what? Perfectly invested, completely opposite to the what? To the motion, which is case number 5. That's why I break them down. Yes, exactly. Friction is the I don't want to say the only culprit here, but it's definitely one of the biggest common 180 degrees against motion forces. That's why I divided it into 5 cases. Many other teachers divide into how many? Okay, can someone tell me why they divide into 3 instead of 5? Can someone tell me what are the 3 cases then? Exactly. So instead of making a 0 and an acute distinct, they combine them together. So they say 0 inclusive, but less than 90. And then what's the case by itself? 90. And then what's case number 3? Bigger than 90, but touching what? I don't like that. I like to explicitly give the 0 and 180 their own distinct cases. Because to me, they are that special. And again, I understood it that way 25 years ago. Made me a physics teacher. Okay? So that means your work here being done is negative, which means it's not with you, it's against you, but it's not the worst that could happen. The worst that could happen, as Nora said, is once you fully go against, which obviously would be an FK situation. Okay, so everyone, I'm going to go to the next slide. There we go. Of course, it's FK. I mean, or by the way, what else other than FK? What could it be? It could be someone legit just pulling like a sled, for example. Okay, or it could be what? Tension as well. Yes, you got it. So can someone tell me why on the cast rule the cosine of 180 is 0? Who would like to answer that question? Who would like to answer the question? Why on the cast rule can you prove that the cosine of 180 degrees is 0? Who would like to answer? You get a laser pointer. Why is it 180? Look at the cast rule. This is not even a grade 12 question. This is a grade 11 functions question. Yes, go ahead, Ammar. Top one. Why is the cosine of 180 a legit -1, no decimal? Exactly. And we said that cosine is what? Horizontal or vertical? And now, are you on the positive side of the universe or the negative side of the universe? You got it. Yes. Thank you. So because now the location is -1. Because now you are still 1 in magnitude, but you're going that way. Nice. Okay, so it's max negative. That is the worst force that could happen to our system because it's sucking as much energy possible from the object. Okay, all right. Go ahead, take your time. We're still doing that. Is this touch screen? Okay. So you click. Okay, then you where is my last cell? What is it? E77. So you just click. Oh, it's already counting everything. You just have to change the last cell. كانت 143 يمكن انت شلت حاجه من لانه yeah C77 هاي واحده انا بعرف she's not patient I can play with my dog former student and Miss Couture I'll give her a ticket she's going to need $10 yeah but that's how you change the equation yes okay everyone let's go to the next slide don't worry you can stay okay so I think you already have this one yes this is already done for you no problem so by the way This is my slide to show you why other teachers do the triple cases. If motion and force are generally what? Actually, by the way, I shouldn't say generally parallel. There's no such thing as generally. I should have changed it from last term. There's no such thing as generally parallel. They're either parallel or what? Or not parallel, which covers all the other cases of not 100% parallel. So we can say what? Generally in the same what? Thank you. Yes. So everyone, take this, remove this, scratch it out, and say generally in same direction. DIR. The work done is positive. Why? Because at some point, this motion is being supported by that force. Okay, we can literally flip the situation and say, if motion and force are generally opposite, yeah, I think we can say generally opposite, okay? Or you can say, if you like to change it as you changed the first one, you can say if motion and force are generally against each other. Against each other. The work done is what? Negative. Why? Because that force is not providing the motion, it's actually resisting it. And then the very last case is the case right in between, which means if motion and force are exactly perpendicular to each other, there is no work done at all or just by that force. Exactly. Everyone, there is work done just by some other forces in the system that are not perpendicular. So I want you to add, there's no work done by that force. Please add that. By that specific force. Other forces probably are doing work because they're either pointing with it or against it. I mean, with motion or against motion. All right, let's do a couple of demo problems, everyone. Okay. Demo problem. Oh, sorry. I hope what's in good. All right. Okay. A weightlifter uses a force. I don't like to use a force. We should say what a force applies a force. So everyone, go ahead and say apply. Or what's the other word of apply that university people like? Starts with EX. Exert. Exertion. So uses means applies a force. You know my stuff. Easy words all the time. I just mentioned the scientific words, so I know that you heard it once. A weightlifter applies a force of 275 newtons to lift weights directly what? Upward. Okay. Through a distance of 0.65 meters. Good. Everything has to be standard. These are physics standard equations. Yes. Great. Yep, you're right. Determine how much work is being done by the weightlifter force. Okay. Do you think we really need an FBD for this? Simple enough. Let's sketch an FBD in general, okay? So, obviously, do I need to sketch a bar and the weight and stuff? No, you just sketch what? You just sketch a box or a dot. Thank you, a dot in university. So, everyone, I'm just going to sketch a what? A 3D box. Okay, definitely. What's pulling down on the box? I mean, what? I mean, the whole idea of resistance training is that you have to what? Go against the force. That's why astronauts cannot train where? In space. What instead? But they still work out. But instead of using gravity to go against, what do they go against? They use what? They use basically hydraulic system, like spring-loaded machine. So instead of what? Instead of pushing against gravity, you're pushing against what? You're pushing against the spring. How many people? Okay, how many people seen those machines at Good Life? The machines where basically you can actually adjust the resistance by actually increasing the air pressure in a tube. How many people have seen that? Yeah, I think because they don't want to like making a weight machine is just a lot of money and also a lot of weight to bring into the club. So instead, they actually basically what build a machine where you actually what keep adjusting it with a what with a button or a dial, and then basically the air pressure in the vent or in the pipe is exactly equivalent to what to pushing against you with 100 pounds or so on and so forth. You see what I mean? There's no weight, but there's a compressor device connected to the what to the machine, and it basically what simulates the effect of going against the force. Make sense? That's kind of exactly what they do in space. They use springs instead of gravity to still what build the muscle. So obviously FG going down. And what's pushing up? F applied. Oh, who said Fn? Said Fn. Again, Fn, if they're lifting the weight this way, right? And you're right. But in general, they're just applying a what? They're just applying a force. Make sense? So always, whenever you want to be safe, just call it F applied. Especially if you don't know exactly the way of applying that force. Okay, which way is the direction of the force? Come on. Sorry, the direction of motion. Up, yes. So motion. Okay. Which work are they asking us to calculate? The work done by gravity or the work done by the applied force? The weightlifter, which means they want the applied force. So let's write the equation. W app, everyone. W app equals force app times delta D. By the way, do you ever need to say delta D app? No, delta D is the same for everything. The only two things that are different for each work is the force and the what, and technically the what, the theta, because each force could be pointing differently as far as the direction of motion is concerned. So I want you to write cosine theta app. Okay, how much force is that weightlifter applying? How much? Just how much? 275 in newtons. So the number is good. I mean, the unit is good. How much distance are we talking about? 0.65 meters. Cosine. Okay, all you have to ask yourself now is one question. The force applied and the motion. What is their angle situation? Like, which case of the 5 are they? That's why I taught you 5 cases. Which case is these two? It is pointing up, but I'm asking you, what can you tell me about the vector for force applied and the vector for motion? They are perfectly what? They are perfectly parallel. What angle is for two exactly parallel vectors? There, you see what I mean? That, by the way, I'm assuming you said 90 because it's pointing up. Yes, it is pointing up. But as far as what? As far as I'm concerned, I don't care where it points. I care where it points relative to the motion direction. You see what I mean? We always have to relate every force to what? To the motion direction of the object. Do you see what I mean? You always relate all the forces to the same motion direction. And then you see what angle each force produces. As long as it's connected tail to tail. Perfect. So obviously it's cosine of 0 degrees because it's parallel. What's the cosine of 0 degrees? Positive 1, which makes sense. This weightlifter is using 100% of their force. Like none of it is being wasted. Great. I need someone to multiply these two. Who's got this? 178.75. Done. That's it. It is joules. Nice. Why? Because first, okay, explain to me using two different arguments that this cannot be Newton. What's argument number 1? Come on. Why can this not be 178.75 Newton? What's the easy argument? It's not a force. It's work. What's another proof? Is there already another number with newtons there? Yes. You can't multiply newtons by meters and still produce newtons. Units change. That's it. So this is joules. Nice. And it's positive because they are pushing the object where it's meant to go, or where it's intended to go. Done. That's it. Okay. The next question, and we're done. A tow truck uses a winch with a rope attached to pull a car that is stuck in a ditch. Okay, that's fine. The rope exerts or applies, obviously, a tension force within it of 9.9 times 10 to the 3, or basically 9,900 newtons. Two sig fig situation. Oh, whoa, sorry, yeah, I totally forgot. My bad. What's the sig fig situation for this one? 3. Hold on, no, 2. By the way, does this apply to the sig figs? No way. Otherwise, it would be no sig figs in the whole thing because this is one sig fig technically. Okay? No, 0 is an exact constant in a way. So this should be what, everyone? This should be 2 sig figs. 180. Yes. Sorry. Yes, 180. All right. Last one. So the angle between the rope and the direction in which the car ends up moving is how many degrees? So if you want to sketch a very quick diagram, everyone, let's say that this is the ditch, right, like this. Everyone, go ahead. Here is the car. Come on. Now, obviously, the car's gonna move this way, right? Could I put the tension like this? Does this make sense? Hold on. If I put the tension like that, it seems that the tension and the motion are going what? Parallel, which means an angle of what? 0. But they're telling me the angle is not 0. The angle is how much? 12 degrees, which means what do I need to do to that tension? I either have to tilt it down or what? Tilt it up. But it has to be 12 degrees from this line shifted here. Okay? Otherwise, it would be what? It would be 0 degrees. And they did not say that. So I have to, everyone, we have to change it to this. Maybe. Okay. Tell me if you think this is okay. Yeah, because if I imagine this as a sight line, this is how much? How much? There you go. You got it. Okay? All right. So let's say this is motion, which means this is tension. Okay? I mean, we can add a bunch of other things to that, FBD, but you know what? That was the whole idea of it, to relate the angle to the motion direction. Okay? Let's start with the equation. WT equals, let me read the question. Determine the amount of work done on the car by the tow truck or by the tension force. So FT delta D cosine theta T. Okay. What's the force applied by the tension? Like how much tension is felt inside of the rope? 9,900 equals 9,900. All right. How much distance did the car move? Sorry, under the application of that force. How much? 4.3 in meters. Cosine. What's the angle between the tension and the motion direction? 12. The cosine is 12. Everyone, should we expect a negative or a positive work for this? Even if we did not have numbers. Is the motion direction and the force somewhat in the same direction? Great. So this is aiding the motion. It's not fully, but it's partially. Great. What's the answer, everyone? And we need 2 stick figs, 2 stick figs, 2 stick figs. In joules, of course. How much? So 41.6. So if you cut it at 2, you should get 42,000 joules or 42 kilojoules or 42 times 10 to the 42 times 10 to the 3 joules, or in scientific notation, done.